Hi everyone. So this is the first video that talks about regularization for deep learning. So that's the start of section 2 of this course. Now that's a very important topic, and that's why we need to dedicate one full video for the introduction of it. So what regularization or generalization means in general is that you want your model to perform well for data that are never seen, that have never been seen during training. And that's a very tricky thing, because how would you know if you've never seen this data during training, right? And in fact, this is even related to a very important concept in philosophy, which has been at the core of machine learning in general, which is called Occam's razor. And what Occam's razor says is that if you observe a phenomena, then any phenomena in life, and you have multiple hypotheses explaining this phenomena, you might have more than one hypothesis. You might have some hypotheses that are consistent all the way with the phenomena. Some hypotheses are not consistent with the phenomena. So what Occam's razor says is that you should pick the simplest consistent hypothesis. So among all the consistent hypotheses, pick the simplest one. Right? So there might be, so for example, all your life and through the history of humanity, you know that the sun rises in the morning, right? So one hypothesis is that the sun will always rise in the morning. Another hypothesis that's consistent with the phenomena is that the sun has been rising in the morning in all the past, but in the future it will not rise in the morning anymore. Right? That's another hypothesis that's consistent, because it also says that the past is correct, right? So it fits the observed phenomena. But that second hypothesis is more complex than the first one. The first one is the simplest consistent hypothesis, right? So now that actually introduces, so I said the second hypothesis is more complex, right? Because this is just, I'm talking about intuition here, right? But to formalize this concept, we actually need a formalization of the concept of complexity of a hypothesis, right? And it will be important in our discussion to distinguish between the complexity of a hypothesis space, which is the space that contains all the hypotheses, and the complexity of the solution or the hypothesis, right? So what Occam's razor says is pick the simplest hypothesis. It doesn't talk about the hypothesis space. Maybe in order to pick a good simple hypothesis, I need actually a complex hypothesis space, right? And I'll come back to that point, the difference between complexity of the hypothesis space and the hypothesis itself at the end of the video. So the definition of regularization, so that's in a nutshell, that's why we need regularization, because we need to choose a hypothesis that generalizes, and that's why generalization is another keyword that's used for regularization strategies. And basically, it's concerned with decreasing the test error. And the test error is the error on the test data, the data that have never been seen during training, right? So that's why it's very important when you design a machine learning strategy is never to include the test data in the training process, because then you would have no guarantee, right? So you use this data to have some kind of a guarantee on the test error. But if you include it in the training data, then there will be no guarantee in the test error. So one way of defining regularization strategy, like when to say that your technique is really not an optimization strategy for training, and it's specifically a regularization strategy, is whenever you do any modification to the learning algorithm that's intended to reduce the generalization error or the test error, but not the training error, then this is a regularization mechanism. So any mechanism whose goal is to reduce the generalization error. Maybe as a byproduct you reduce the training error, but that was not the objective of the algorithm, right? So the common ways of doing this is through what? You may add constraints on the parameter values, right? So you restrict your parameters to have certain values, like for example adding explicit constraints, such that saying the magnitude of the weights have to be less than a certain value, Or another way is having norm penalties, which is adding a regularization coefficient multiplied by some factor that penalizes the choices of higher magnitudes of weights. And you add that to the cost function, right? Now, these constraints are designed to encode prior knowledge, prior belief about the system, right? In the sun rising example, my belief is that what's been happening for 10 million years or even more will be happening in the future, right? So that's a constraint on the hypothesis that eliminates that second complex hypothesis that we talked about. And this constraint encodes prior knowledge or prior belief about the solution. So they are also, they can be designed to express a generic preference for a simpler model. And that's basically to reflect what we said about Occam's razor, because this actually serves as the main inspiration for regularization techniques, is that you pick a model that is simpler, will generalize better, right? So for example, if I have some data, right, that looks like this in a space, then picking a line can be considered a result of a regularization strategy, because the other hypothesis that may be more complex is to exactly fit the data. And that's what we call overfitting, because if it turns out that the test data do not follow this pattern as well, right? But of course you could be wrong, and maybe the test data are following the more complex pattern. And I'll come back to this example, because that's actually, in this case, we didn't choose a hypothesis that's consistent with the data, right? So we increased the training error, right? So even though we're trying to mimic Occam's razor, sometimes we increase the training error at the cost of simplicity. And the reason is that in most cases, we don't have a guarantee that this training data is perfect, right? So there could be noise in the data generating process for training labels itself. So that's why we could choose the line over the exact fit, more complex curve, right? Another group of regularization strategies may not necessarily put the constraint in an explicit or even as a norm penalty, but having multiple models that put pressure on each other. So for example, I could train multiple different models and put a constraint that these models have to agree, or the majority of these models have to agree. And these are called ensemble methods, right? So as we said, we might even increase the training error, right? What we increase, and usually the error decomposes into two parts: bias and variance, right? And the bias, you can think of it as basically a difference in expected value. So it's the difference of the expected value of the prediction of the model minus the expected value of the true labels, right? So I might not set that to 0. I might choose a solution that have this a non-zero value at the benefit of reducing variance. And variance is the change in error from one example to the next, right? So when I reduce variance, I reduce the sensitivity to the realization of the examples, and hence I expect the model to generalize better, because it's doing almost the same for different examples, so it will do the same for examples that I haven't seen before. Now, a very famous term in regularization is overfitting. And overfitting refers to, for example, here, exactly fitting and ending up with a very complex solution that doesn't generalize well, right? So overfitting could happen in different ways. One of the ways is that the model family being trained can include the true data generating process as well as many other possible data generating processes, right? And in the overfitting regime, you are afraid basically that you would choose one of these other processes, right? Now, this can happen in many ways. So, for example, I could even, let's revisit that other example. Maybe my data lies over a line, right? So one assumption is that I could choose the line, and another assumption is I could still have a curve that fits the data, right? And here actually you have an exact interpretation of Occam's razor by picking the simplest consistent hypothesis instead of the more complex one, right? In some other cases, maybe I can't even fit the training data, right? And maybe I cannot include the true data generating process. Maybe I don't know how, right? So maybe that's out of the question. Maybe my model is not capable of exactly coming up with the true data generating process. Remember, distinguish between the true data generating process or distribution and the training data. The training data captures it. And we hope that if the training data do not have a bias and there are many enough of them, then we capture the true data generating process. But in general, the training data has an empirical distribution that comes from the true data generating process, right? So in some cases, we can't even, our model is not capable of modeling the true data generating process. And in this case, generalization or regularization is used to approximate as much as possible, right? Before concluding this video, I want you to have this thought exercise. If regularization suggests choosing simple solutions, then why is it the case that deep neural networks have large number of parameters typically? And while you're thinking about this, the answer to this question, I think it will suggest you a lot of ideas that I don't even have in mind right now, but I think it's a good question, and it's a good question to think about. And one angle I think is useful when thinking about this question is to distinguish between the complexity of the hypothesis space, which is given by the number of parameters in the network, the model family that the network can represent, and the complexity of the final solution, the exact solution, right? Also remember the exercise we had before where we said check out any network that works and see the sparsity pattern in the nonlinear activations, because that tells you how complex is the final solution. Maybe the network has 100,000 nonlinear activation units, but the final solution will only have 1,000 of them active, right? So even though the model family can be very, very complex, the final solution can be very simple, right? In fact, complexity of the hypothesis space or complexity of the model could give you power, more power to have simpler solutions, right? And I'll come back to that point. That point is a very important one. Complexity of the model, the expressive power of the model can actually make you reach simpler conclusions. And we will come back to that idea later in the course. Thank you.